Alright, so we're going to begin our foray into Chapter 4 with Section 4.1, Related Rates. Pretty much everything in the book that you read was just examples. They just jumped right in with examples, so there's really not a whole lot for me to lecture on. There's really not a whole lot of theory or anything that we need to be able to do some of these problems. So I'm going to just jump into some examples of my own out of the homework section that'll be similar to homework problems that you find. Let's go ahead and start with number 4. You can see in number 4 we have the length of a rectangle is increasing at a rate of 8 centimeters per second. Its width is increasing at a rate of 3 centimeters per second. When the length is 20 and the width is 10, how fast is the area of the rectangle increasing? So it's always a good idea to draw a picture. And so here we have a rectangle, and we have our length here, L, and our width here, we'll call that W. So label the sides that we know. Now what are we told? The length is increasing at a rate of 8 centimeters per second. So that means that dl dt, the change in L with respect to time, is 8 centimeters per second. Alright, and that's positive because it's increasing. The width is also increasing. So the change in the width, dw dt, is 3 centimeters per second. Okay, so let's write down what we know. That's what's given to us in that first sentence there in number 4. It says when the length is 20 and width is 10, how fast is the area of the rectangle increasing? So we want to find the derivative of the area with respect to time when, again, the length is 20 centimeters and the width is, 10 centimeters. Okay, so it says how fast is the area changing with respect to time at that point. Alright, so what we're going to need first of all is an area formula, and you can see the area is equal to length times width. Okay, and so we're going to use then the chain rule, since we're thinking of L and W both as functions of time, to find dA dt. Now, what does that tell us then? That dA dt is going to equal, well, the derivative of A with respect to t is going to be, let's see, it's going to be how fast the area is changing with respect to width. So that's going to be, alright, we got to use a product rule here when we differentiate this right side. We've got two functions multiplied together. Two functions of t basically. So we have the left side, of course, is just dA dt. We have the first, L, times the derivative, dw dt, plus the second, w, times the derivative of the first, which is dl dt. So we got everything we need then to find dA dt. We can see that dA dt is going to be, well, let's see, at the point where, what would we have? L is 20. L is 20 and W is 10 is going to be, well, L, which is 20, times dW dt, which we were told at the beginning, remember, was 3 centimeters per second, plus W, which is 10 at this instant, times dL dt, which we're told originally, I think, was 8. Is that right? Yeah, 8 centimeters per second. And what do we get then? We get 20 times 3 is 60 plus 80. We get 140, and the unit on that is going to be, what's it going to be? Well, remember, this was centimeters here, so if you look at what our units were, this was the length, which is given in centimeters. This was centimeters per second. This was a width, which is given in centimeters. This is centimeters per second. So we have centimeters times centimeters per second, and we get centimeters squared per second. Let me rewrite that. Our final answer is 140 square centimeters per second. That's how fast the area is increasing. dA dt, it's the units of area over the units of time, square centimeters per second. Alright, so there's an example of how we can do that one. Let's try another example. Let's go ahead and take a look at number 6. Number 6, we are given that x squared plus y squared equals 25. So we have this relationship. You should recognize that as the equation of a circle of radius 5 centered at the origin. And we have dy dt equals 6. So we're given that information. The change in y with respect to time is equal to 6. We want to find, in this particular problem, dx dt at what point? When y is equal to 4. When y is equal to 4. Okay, so let's go ahead and differentiate both sides with respect to t. We're thinking of both functions, x and y, as functions of t. So if we take the derivative, so we're going to differentiate both sides with respect to t, starting with this formula right here. The derivative of the left side is going to be 2x times the derivative of the inside by the chain rule, which is dx dt, plus the derivative of y squared, which is going to be 2y times dy dt. What's the derivative of the right side? Well, it's a constant on the right side, so that's going to be 0. What are we looking for here? We're looking for dx dt, so we're going to solve this equation for dx dt. And if we do that, we have 2x dx dt is equal to negative 2y dy dt, And so dividing both sides by 2x is going to give us what we want. We have coming up here then that dx dt, and we solve for that on the left side of the equation, is going to equal what? The negative 2, and the 2 will just give us a negative y over x times dy dt. And so now we can evaluate dx dt at the point we wanted when y was equal to 4. And so you notice that we're going to have an x in here. When y is equal to 4, what is x going to be? We have negative 4 over, what is x at this point, times dy dt, which we're told is 6. Well, we need to find out what x is at this case, in this situation. So if we come up here and we start with the situation where, what do we say? Y is equal to 4, x is equal to what? Well, we're just going to use our equation. X squared plus 4 squared has to equal 25. So x squared is equal to 25 minus 16, which is 9. X is, we'll say, positive 3. It could be positive or negative 3. And so let's assume it's positive 3. Then we can erase this down here. So we should have really a plus or minus 3 here. If it's positive, we're going to get negative 4 thirds times 6, or let's see, 6 over 3 is 2, negative 12. So we could also get a positive 12, depending on if we use a positive or negative 3 here for x. So plus or minus 12 is going to be dx dt. We can either think of it as decreasing or increasing. Again, depending on the value of x that we have here, and usually most situations for these related rates you have story type problems where you know whether the x value is going to be positive or negative. Alright, let's try another example. Next thing I want to look at, let's look at number 11. We may not do the whole problem here, but at least set it up. We have a plane that's flying horizontally at an altitude of 1 mile and a speed of 500 miles per hour, passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when it is 2 miles away from the station. Alright, so let's draw a picture here. It's always good to draw a picture. So here's a plane. And, I know that you guys probably aren't as good at artists as I am, because I can really draw good planes. Here it is. And it's flying this way at a rate of 500 miles per hour. It is 1 mile off the ground. And we got ourselves a little radar station here, which I think most of the time that they're in purple, radar stations are. Okay, so let's see. The plane flying horizontally, altitude of 1 mile, speed of 500 miles per hour, passes directly over a radar station. Let's go ahead and put our radar station over here first of all. So here's our radar station. Alright, let's take it out over here. We don't want it on there. Alright, so going at a rate of 500 miles per hour. Then what do we want to find out? Find the rate at which the distance from the plane to the station is increasing when it is 2 miles away from the station. So as our plane moves along, at some point here, the plane is going to have a distance, which we'll call d, of 2 miles. When that's the case, we want to find, let's see, we probably don't want to call this d. Let's call this instead, how about, I don't know, let's just call it a. No, let's call it c, because it's going to be the hypotenuse of a right triangle. Let's call it c that we're trying to find. We want to know when c is 2 miles, what is dc dt, the change in c, which again is the distance from the radar station to the plane with respect to time. Alright, well, we can think of this again as being a right triangle here. And so we know if we make a right triangle out of this, that this leg right here is 1 mile. Alright, so assume there's no height to the radar station, so that's 1 mile on that leg of it. And so we don't know what this distance here is, x. But we do have a relationship between x1 and c. We know that x squared plus 1 squared is equal to c squared, because again we can think of this as a right triangle. So we're trying to find dc dt. So let's go ahead and differentiate this with respect to time. So we have 2x dx dt plus, well, this is a constant here, so it's not changing at all. That's 0. On the right side we have 2c dc dt. And so solving this for dc dt gives us that dc dt, the change in our distance from the plane to the radar station with respect to time, is equal to, let's see, if we divide that, we're going to have x over c times dx dt. So we have a couple of things we need to find out. First of all, we need to find out what is x at this point and how fast is x changing at that point. Alright, well, we know how fast x is changing. No matter what we are here, since the distance since the plane is flying at a rate of 500 miles per hour, we can see that dx dt is exactly 500. That's how fast our x variable, the horizontal distance of the plane, is changing. So we know that piece of the puzzle. Now we need to find x. Well, we need to find x when c is equal to 2. So over here, we're going to say we want to find x when c is equal to 2. So we're going to have that x squared plus 1 squared equals 2 squared. Alright, and so we're in business then. That x squared plus 1 is equal to 4. X here is 3, and so, x squared is 3. X is the positive square root of 3. Here, since we have a situation where we know x represents a distance, we know that x is the positive square root of 3. So we're going to take that number then, and we just go ahead and plug it in. I'll leave the rest to you here. Again, we're going to take x over c times dx dt. That'll give us dc dt, which again is what we're looking for. How fast that distance, which we called c, is changing at the point when the distance is exactly 2 miles. So you're going to plug your square root of 3 in for x, your, 2 in for c, and dx dt, as we said, is 500. Alright, let's set up another one or two of these. Next one we'll look at is number 15. This one just takes a little bit to get set up, I think. We have a man starts walking north at 4 feet per second from a point P. So let's get a point here in the middle. Let's call this P. And the man is walking north at 4 feet per second. And then what do we know? 5 minutes later, a woman starts walking south at 5 feet per second from a point 500 feet due east of P. So if we go 500 feet to the east, again, assuming north is up here. So we go 500 feet to the east, and then a woman is walking due south at a rate of 5 feet per second, but she starts 5 minutes later. 5 feet per second, due south, the woman is walking there. So we want to find, what do we want to find here? What rate are the people moving apart 15 minutes after the woman starts walking? 15 minutes after the woman starts walking. So, all right, we're looking for, let's see, what are we looking for? The rate they're moving apart. So again, we call this distance here from one person to the other c. We want to find dc dt when what? When t is equal to, let's see, 5 minutes after the woman starts walking. Well, if we say t equals 0 is when the man starts walking, so t equals 0 is when he started going. 5 minutes later goes by, so now we're at t equals 5. 20 minutes after that is going to be at 25. So we're going to say t is equal to 25. Again, starting t equals 0 is when the man starts walking. Alright, so dc dt when t equals 25. Well, again, we can think of c as the hypotenuse of a right triangle. What I'm going to do is I'm going to extend this triangle down this way. And what do we know? Well, we know this length of the hypotenuse, or this leg of the triangle, I should say, is 500. Alright, what about this? Well, let's call x the distance that the man is walking from the point P. We'll call that x, and then we'll call this distance over here, we'll call this distance y. That's the distance that the woman is south from the point P. So not counting the 500 feet to the east, just this distance that she's traveled south. So it would be this part right here. Alright, what do we know then? We know that x plus y quantity squared plus 500 squared is equal to c squared. So everybody see where I got that. Here's the x, that's the distance the man is from the point P. Y is the distance the woman is from the point P, in the south direction. And then this 500 here is how we get our right triangle. Now we're going to differentiate this with respect to t. Alright, so we're going to do 2 times the quantity x plus y times the derivative of what's inside. Well, the derivative of x is dx dt. Derivative of y is dy dt. So using the chain rule there. And then the chain rule also for the dx dt and dy dt. 500 squared is a constant. It's a big constant, but still a constant. On the right side, we have 2c times dc dt. So let's see if we can solve this equation right here for dc dt, which is what we're trying to find. So I got 2x plus 2y times dx over dt plus dy over dt, or dy dt, is equal to 2c dc dt. So all we have to do is divide both sides by 2c. Okay, so we have our equation for dc dt. dc dt is equal to 2x plus 2y times dx dt plus dy dt all over 2c. So we need to find some things. We need x, we need y, we need dx dt, we need dy dt, and we need c. Now dx dt and dy dt we are given. dx dt is 4 feet per second. That's the change in x. And y, which is increasing, the value of y is increasing, is 5 feet per second. So we're given that. So we have the dx dt is 4, again, feet per second. dy dt is 5 feet per second. So that added together is going to give us a combined change in that one leg of our hypotenuse. Let's see, what about dc dt? Well, that's what we're trying to find. What about c at this point? Well, let's see, when t is equal to 25, how far is x? X is going to be 4 times, let's see, this person's been walking for 25 minutes, right? So 4 times 20, I'm sorry, I almost got thrown off by the units here. This is 4 feet per second, 25 minutes, right? Because we're going, oh, no, 20 minutes. 20, okay. Let's back up here. T is not 25, is it? We want to know, look at the problem again. What rate are the people moving apart 15 minutes after the woman starts walking? Well, the woman starts walking 5 minutes. T equals 5 at this point from the time the original person starts walking. So that's going to be 20 minutes. 20 minutes. Now, we also have an issue here with minutes, and our rates are given in terms of seconds. So 20 minutes is equal to 20 times 60, which is 3,200 seconds. Is that right? No. How about 1,200 seconds? I'm not doing so good on this problem. You guys still with me here? 1,200 seconds. All right, so everybody understand why I did that? Because our rates are given in terms of feet per second, and our time is given in terms of minutes, so I had to convert that to seconds. So 20 times 60 is going to be 1,200 seconds. So, when t is equal to 25, how far has Mr. X traveled here? Going north. Well, he's been walking 4 feet per second. He's been doing that for all 20 minutes, so that's for 1,200 seconds. So that's a total of 4,800 feet that he has traveled. Now, what about y? Well, y, if we come up here, how far has she been traveling? Well, she's been going 5 feet per second, but she's only been doing so for 15 minutes, right? Because she started 5 minutes later. So we need to take 15 times 60. 6 times 5 is 0, 3, 6. That's 900 seconds. So 900 seconds. And that gives us a total of 5 times 900, which I think is 4,500 feet. Whew. Okay. Now we can figure out what c is. So at this moment in time, 15 minutes after the woman starts walking, which is 20 minutes after the man starts walking, because the woman started walking 5 minutes after the man, converting that to seconds, multiplying that by the rate per second in which these each are walking, we have that when t is equal to 20 minutes, x was equal to 4,800 feet, y was equal to 4,500 feet. Everybody with me on that? Is that right? Okay, 4,500 for y, 4,800 for x. And so now we can use this formula right here to find c. So we're going to use that to find c from the fact that x plus y squared plus 500 squared is equal to c squared. Again, that's just a Pythagorean theorem. So I'll put 4,800 for x, 4,500 in for y. Solve for c. Once we know c, then we got everything we need. We would just have found c. We know what x is 4,800, y is 4,500. This is all in feet now, so dx dt is 4 feet per second, dy dt is 5 feet per second. And putting all that in should give us dc dt at that moment in time. All right, so I hope that wasn't too confusing for everybody. But again, it's just a matter of getting that formula relating the variables that you know to the variable that you're trying to find. So getting this equation right here was key, and then finding dc dt based on that allowed us to get where we wanted to go. All right, finally, last problem. Let's look at 24. I know this video is getting a little bit long, but we've got a pool. Let me go ahead and draw a picture of the pool here. Let's see what we can do about this. We want to find, again, basically how fast the water level is rising. So we're looking for dH dt. We aren't given something. We're given that the pool is being filled at a rate of 0.8 cubic feet per minute. So we're given that dV dt, the change in the volume with respect to time, is 0.8. Again, that's given in cubic feet per minute. We want to find the change in the height of the water, dH dt, when, let's see, when the height at the deepest point, depth deepest 5, when h is equal to 5. So what we're going to do is we're going to say, all right, let's call this height here h. All right, so the height of the water is going to be called h. The height to the deepest point will be called h. All right, so basically what you can think of this as being a parallelogram. And remember that the area of a parallelogram, well, let's see, not parallelogram, what are those called? It's called a rhombus, maybe? Well, the area is equal to height times base 1 plus base 2 over 2. So do you remember that the area, if you have a, I forget what these are called, base 1, base 2, and a height h, the area of this four-sided figure is you add the two bases together times the height and multiply and divide by 2. Okay, so that means that if we take the volume of this thing, the volume of this pool, the water, is going to be, well, let's see, it's going to be 1/2 times, we'll do the area of this parallelogram. Well, this is a 12-foot base here, so that's 12 times, let's see, let's call this section of it, well, let's call this whole area right here B. Alright, so this is all B, and that's just going to be the width of the water level. So let's see, we want 12 plus B. What am I doing here? We want to erase that. 12 plus B. Okay, times the height, which we're calling h. But then the volume is going to be times the width of the pool, and we're told that the width of the pool is 20, and that's a constant width. So that's going to be 20. There's our formula for V. But now the problem is we want to get both B, well, we need to get B in terms of h. So what we're going to do then is we're going to say, all right, well, let's call this little section here, let's call this x, and let's call this little section here, let's call this y. All right, now what's the relationship between, well, between h and x? Well, notice that this is 6 feet here. If this was all the way full, we'd have 6 feet here by 6 feet here. Remember that this is 6 feet. And then we have a little bit of 3 feet tacked on here, which we don't really care about. So the ratio of x to h is going to be the same. This is going to be a little equilateral triangle here. So we could say that, let's just do it up here, x over h is going to equal 6 over 6. In other words, x is going to be equal to h. X and h are going to be the same thing. Now, what about y here? Well, let's see, this is a total of 16 feet. So if this was filled all the way up, we would have a 6 feet height by 16 feet. So y over h is going to be equal to 16 over 6. It has to be that same ratio by similar triangles. So again, what we're saying here is if we filled this all the way up, this little triangle right here, we'd have 6 feet height by 16 across. And so the y value here and the h value here have to be the same ratio. Now, if we solve this for y, it tells us that y is equal to, see, 16 over 6 can be reduced to 8/3 times h. Alright, now what is b equal to? Well, b is equal to this distance of 12 here. So let's see. It's this distance of 12 feet here plus y plus x. That's the base of the top part of this parallelogram. Or rhombus, or trapezoid. Trapezoid is what it's called. So b is equal to 12 plus x plus y, which is equal to 12 plus, what is x? X is the same as h plus y. What is y? It's the same as 8/3 h. So we can replace b in our volume formula with 12 plus h plus 8/3 h, or 12 plus, let's see, that'd be 3/3 plus 8/3 is 11/3 h. Okay, that's what goes in for b. So coming down here now, we can get our volume. Our volume is going to be 1/2 times 12 plus b, which is 12 plus 11/3 h. All that times h, all that times 20. Alright, so let's take 20 over 2 to get 10. 12 plus 12 is 24, plus 11/3 h times h. Let's go ahead and distribute the 10 and the h, so we're going to get 240 h plus 110 over 3 h squared. And now we're ready to take dv, this is what v is equal to, dv dt. What's that equal to? Well, that's 240 times the derivative of h, which is dh dt, plus 2 times 110 over 3, that gives me 220 over 3 times h times dh dt. And so solving this for dh dt, it looks like we have that dv dt is equal to, see, 240 plus 220 over 3, 220 over 3 times h times dh dt. And so solving this for dh dt, as we said, we'll put it on the left here, it's equal to dv dt divided by 240 plus 220 over 3 times h. Now at this point, what are we looking at? We're looking at when h is equal to 5 feet, remember? And remember that dv dt was equal to 0.8. It was changing at a rate of 0.8 cubic feet per minute. So our dh dt is going to actually be in feet per minute. That's how fast the height of the pool is changing. So you should be able to just plug that in and go from there. So your numbers will probably be a little bit different on the problem you have, but you should be able to get through it. Alright, so a couple problems I didn't do, but I think you should be okay if you read through the examples in the book as you already have and look over these examples. Please let me know if you have any questions. The password for 4.2 or 4.1 is, the word is reify, R-E-I-F-Y, which means to give a concrete form to something abstract, to make some sort of abstract, something abstract into something concrete. Alright, good luck on your homework.